Welcome class 9. Today's topic is gravitation. We know that if an object is released from a certain height, it will fall down towards the center of the earth. The force by which any object is pulled towards the center of the earth is called the gravitational force. So let's say that there are two objects of masses m1 and m2 respectively. Now the force of gravity in between the two bodies will depend on the masses of these two bodies. If the masses of the bodies are more, then the force of gravity in between the bodies will be more. And again, if the bodies have the masses less, then the force of gravity in between the bodies will also be less. So we can say that the force of gravity between the two bodies is directly proportional to the product of their masses, and this can be represented mathematically as F proportional to m1 into m2. Again, the force of gravity will also depend upon the distance between the two bodies. If the two bodies are in the distance r away from each other, then it will have a certain amount of force of gravity between the two bodies. But if the bodies are separated again by more distance, or if we say the distance between the bodies are increased, then the force between the two bodies will now decrease. So more the distance, less will be the force, and less the distance, more will be the force. So in this case, the force is inversely proportional to the square of the distance between them. And with this can be represented mathematically as F proportional to 1 by r squared. Now since force is equal to product of m1 and m2, and also force is inversely proportional to the distance between them, so F is proportional to 1 by r squared. So together we can write these two expressions as F proportional to m1 m2 by r squared. Now the sign of proportionality can be replaced by equals to sign by multiplying the expression with a constant value. Over here g is the constant value. So this expression can be rewritten as F equals g into m1 m2 by r squared, where g is known as the gravitational constant, which remains same at all places irrespective of temperature, pressure or altitude, etc. It is also known as the universal gravitational constant. Now if the two bodies have the forces of gravity acting in between them, then m1 will attract m2 towards itself, and m2 in turn will attract m1 towards itself. So the two forces by which these two bodies will attract each other will be of equal magnitude. So over here F represents equal magnitude of forces by which the two bodies will attract each other. So m1 attracts m2 towards itself with the force of F, and m2 attracts m1 towards in this direction with the force of F. So we can say that F12, that is force applied on body 1 by body 2, is in this direction, that is force on this body by this body, that is F12 in this direction, is equal to force applied on the second body because of the first body is in this direction. Although they are equal in magnitude, even though their directions are different. Since force is a vector quantity, so they will have specific directions. So this can be written as F12 equals minus of F21. Minus indicates the opposite directions. So here the two forces are the action reaction pair. So if one of the force is action, the other one will be the reaction. So it is an action reaction force. A particle exerts a force on other particle equal and opposite to the force or the other particle exerts on it. Unit of universal gravitational constant. Since we learned that F is equal to G into m1 m2 by r squared, we can write this expression as G equals F into r squared by m1 m2 by simply cross multiplying r squared with F and bringing m1 m2 in the denominator. We'll get F into r squared by m1 m2. So here the unit of G is equal to, unit of force is Newton and unit of distance is meter. So r squared becomes meter squared. Unit of mass is kg. So m1 m2 becomes kg into kg. So SI unit of G will be equal to Newton meter squared per kg squared. And the value of universal gravitational constant G is equal to 6.67 into 10 to the power minus 11 Newton meter squared per kg squared. Now also, since G is equal to F into r squared by m1 m2, if m1 becomes equal to 1 kg, the mass of first body is 1 kg and mass of second body is 1 kg, and the distance between the two bodies is 1 meter, then we can replace these values out here as F into 1 squared by 1 into 1, where simplifying this you'll get G is equal to F. That means gravitational constant G will be numerically equal to F. That is, it will be numerically equal to the magnitude of force of attraction between two masses, each of 1 kg placed at a separation of 1 meter. Force due to Earth's gravity. Now, since any object, if released, falls towards the center of the Earth, then let's assume that this Earth has the mass of m, capital M, and if the mass of any object is small m, and since the object will be on the surface of the Earth, and since we are measuring the distance from the center of the Earth to the Earth's surface, then the distance of the object from the Earth's center will be the radius of the Earth, that is capital R. So the force acting on that object will be equal to F equals G m into small m by r squared, where capital M is the Earth mass of the Earth and small m is the mass of an object. So if the mass of the Earth is 5.96 into 10 to the power 24 kg, and we know that radius of the Earth has been calculated as 6.37 into 10 to the power 6 meter, and we assume if the mass of the object is 1 kg, then in this relation, if we substitute these values as G, the universal constant, okay, universal gravitational constant is 6.67 into 10 to the power minus 11 into 5.96 into 10 to the power 24, that is the mass of the Earth, into the mass of the object, that is 1 kg, by the radius of the Earth squared, 6.37 into 10 to the power 6 whole squared. If you simplify this, then this will be equal to 9.8 Newton. This means that the Earth attracts a body of mass 1 kg by a force of 9.8 Newton towards its center. So this simplifies that if the Earth attracts any object towards the center of its center, then not only the not only the object is pulled towards the earth, but also the earth will be pulled towards the object. But over here, since the mass of the earth is quite huge compared to the mass of the object, and so the inertia of the earth will be more, so its inertia will not allow the earth to move towards the object, rather the object will move towards the center of the earth.